At this point, we have to integrate the right-hand side. And that's like one of those fairly tricky integrations, which makes it a bit, adds to the level of difficulty of the problem. If you complete this square, you would get, at the bottom, you get x minus 3 squared minus 8 to the power of 3 halves, and then x plus 1. Now, you would have to use one of these trig substitutions. So if you take x minus 3 to be root 8, because I have something squared minus 8, I'm going to do root 8 for that. And my objective is to use secant formula. So I'm going to use secant of theta because secant squared minus 1 is tan squared. So I'll substitute that by secant of theta. So that gives me dx equals, so that would be root 8 secant theta tan of theta d theta. So I can take that and plug it into the integrand and evaluate the integral. So let's see what we get. So x is 3 plus root 8 secant of theta. So that becomes x plus 1 becomes 4 plus root 8 secant of theta divided by, so at the bottom I have 8 times secant squared minus 1, which is tan squared. So tan of theta divided by tan squared of theta divided raised to the power of 3 over 2. And then dx becomes root 8 secant of theta tan of theta d theta. We're going to simplify this one. So at the bottom I have 8 root 8. One of the root 8s cancels. One of the root 8s cancels. We get 1/8. Then I have tan cubed. One of the tangents cancel. And I'm going to get the integral 4 plus 2 root 2 secant of theta divided by tan cubed. So that becomes tan squared times secant of theta d theta. Okay, so if we simplify that further, we're going to see what we get. So the first term becomes 4 over 8, if I take out the 4, secant over tan squared. Tan squared is sine squared over cosine squared. One of the cosines cancels, and we're going to get cosine of theta over sine squared theta d theta. So that's one of those terms. The other term is going to be 2 root 2 over 8 times the integral secant squared, which cancels with the denominator. We get 1 over sine squared d theta. So both of these are fairly easy to integrate. So that's 1/2. The first one is going to be negative 1 over sine theta. Because the derivative of 1 over sine theta becomes negative 1 over sine squared times cosine, and I need another negative sign, plus root 2 over 4. So that is cosecant squared, and that's the derivative of that is the derivative of negative cotangent plus a constant. So that's what I get at the end as the integral of that. But going back to this, what I had was x minus 3 was root 8 secant of theta. So I have to plug it back into here. So if I take theta to be this angle, what I know is that cosine of theta is root 8 over x minus 3. So the hypotenuse is 8, hypotenuse is x minus 3, adjacent is that, and the other side is x squared minus 6x plus 1 square root of that. So that's the other leg. And I can substitute that here. I get 1/2 times minus 1 over sine. So I have to do hypotenuse over opposite. So it's minus x plus 3 over root x squared minus 6x plus 1 plus root 2 over 4 minus cotangent. So that becomes, I guess I'm going to put the negative sign in front. And cotangent is, so cotangent is adjacent over opposite, which is root 8 over root x squared minus 6x plus 1. So if you simplify that, you can factor a root 1/2, taking the common denominator. So these are going to cancel. I get minus x plus 1, because that becomes 2 over square root of x squared minus 6x plus 1 plus a constant. So finally, this is the integral that I get. So I don't necessarily need the constant, so I have to somehow get rid of the constant by some values of f. So bottom line is I get f of x times that equals, so x over square root of x squared minus 6x plus 1 times f of x becomes this entire thing that I found here. So 1/2 times 1 minus x over root x squared minus 6x plus 1 plus a constant. So we'll plug in the values. Since this is a power series centered at 0, 0 would be a good option. So if you plug in x equals 0, you get f of 0, which is exactly a0, is equal to, on this side, you get 1/2 plus c. And eventually, we're going to get f of 0. Oh, sorry, this is 0, not f of 0, if you plug in 0. So you get c cos negative 1/2. And that gives us exactly what f of x is. So f of x becomes, so root x squared minus 6x plus 1 over x multiplied by 1/2 times 1 minus x over root x squared minus 6x plus 1 minus 1/2. So we simplify that and we get f of x is equal to, so at the bottom I'm going to have a 2x. The square roots cancel. I get 1 minus x on top, and I get minus square root of x squared minus 6x plus 1 at the bottom. So essentially, this is the power series. So bottom line from all of what we did is that a n x to the power of n is in fact equal to 1 minus x minus root x squared minus 6x plus 1 over 2x. There are some issues you have to be careful about, which is maybe this power series is not convergent at all. So because we are taking the derivative and we're integrating and things like that, you need to make sure that this is in fact convergent somewhere within some interval around 0, even if it's a small neighborhood, but you do need to make sure it converges. That is not very difficult to see, given that if you look at the square root, we do have a we don't have the binomial theorem for that. So if you take 1 plus x squared minus 6x to the power of 1/2, the binomial theorem tells us that this is 1/2 choose n times x squared minus 6x to the power of n equals 0 to infinity. But this is valid if x squared minus 6x is less than 1. So we can make sure that x is very small in a way that this difference is less than 1. So if, for example, your x is less than, let's just say 1/10, then that may not be the best interval, but it is some interval. I don't really care about how small the interval is. Then x squared minus 6x, which is absolute value of x minus 6, is going to be less than 1/10 times, and this is less than 6, which is less than 1. So anything between -1 and 1 gives you a convergent power series here, and this equality does hold. So over that interval, we can in fact show that our sequence satisfies this equality. In other words, this is in fact a generating function for us. Okay, so we have done all of that and we haven't even shown that an is an integer. So how are we going to deal with that? As I said in the beginning, it would be nice if we can find a better recursion in a way that that recursion tells you that in fact it is integer, something without a denominator. So let's go back and see what we did. What we got is 1 minus x squared minus 6x plus 1 divided by 2x. Okay, so what I'm going to do is I'm going to try to find another recursion by not using what I have here, because then if you use these, then you'll have to expand that, and then you'll have to show that in fact those outcomes that you end up with are going to be integers. And maybe that's possible, but I haven't tried that one, so I'm going to do it slightly differently. So you're going to have a little bit of difficulty if you want to find an explicitly and then show that in fact those are integers, but it's possible, potentially possible to show it that way. Instead, I'm going to try to find a recursion again. So I'll cross multiply, subtract 1 and x, and then square so that I am able to find some recursion. Because if I square, then I can find some relation between f of x and itself, which in turn gives me a relation between an and itself. So this gives you 4x squared f of x squared plus 1 minus x squared plus 4x f of x times minus 1 plus x equals x squared minus 6x plus 1. So we're going to simplify that and see what we get. So we get 4x squared times f of x all squared, 1 minus 2x plus x squared, 4x f of x times x minus 1 equals x squared minus 6x plus 1. So the plus 1 cancels, that's nice. X squared cancels, and everything has a factor of 2x, so I can divide off by that. So in fact, everything, if I cancel this one, I get negative 4x. In fact, everything is going to have a factor of 4x, which is nice. So x, f of x squared, plus f of x, x minus 1, equals negative 1. Okay, so that's nice. I can look at now coefficient of x to the power of n, perhaps n plus 1. So what does that give me? I have to look at the coefficient of x to the power of n here. That gives me the sum, because you're multiplying f of x with itself, you're going to have to multiply. So let me show you in details how you can obtain the coefficient of x to the power of n. So for coefficient of x to the power of n in f of x squared, you can take a0 plus a1x plus a2x squared and so on, and square that. Now, if you want to get x to the power of n, you have to either multiply a0 by an, or multiply a1 by an minus 1, or all the way to going back to an minus 1 by a1 and an by a0. So that gives you a coefficient of x to the power of n. And there's an x in front of that, so that produces x to the power of n plus 1. Plus coefficient of x to the power of n, n plus 1 in the next one is going to be just coefficient of x to the power of n in f of x for x part, and then minus an plus 1. And that is 0, assuming that n is at least 0, because there are no powers of x on the right side. That's perfect, because that exactly gives you what f of what we wanted. So we get an plus 1 is equal to an plus this sum, ak, an minus k equals 0 to n. So then we can use induction to show that in fact everything is integer, because that doesn't have any denominators. Okay. So of course this is going to be quite challenging to write up, because it's quite long and a bunch of integration. It's really long. So how are we going to turn that into a write up in a way that we don't give a headache for the grader, because we don't want to write down something that reduces our chance of getting points. Instead of repeating all of that, which would also take me a lot of time to write, I'm going to basically focus on the most important aspects of my proof, which is this differential equation. If I can show that f of x that I found satisfies this differential equation, then I'm done. Then that means the coefficients of that power series satisfy what I want, satisfy the recursion. And on top of that, I need to show that in fact it satisfies the last recursion. So I'm going to start my solution with writing down the power series that I got. So let f of x be, I obtained that here. 1 minus x minus root x squared minus 6x plus 1 all over 2x. So let f of x be 1 minus x minus root x squared minus 6x plus 1, all of that divided by 2x. Okay, so note that root x squared minus 6x plus 1 is equal to the sum 1/2 choose n, x squared minus 6x to the power of n equals 0 to infinity, by the binomial theorem, as long as absolute value of x squared minus 6x is less than 1. Thus, if absolute value of x is less than 1/10, then absolute value of x squared minus 6x, which is absolute value of x times x minus 6, which is less than 6/10, which is less than 1, then f of x has a power series centered at 0. So I guess I'm just gonna have to check the 0 at the bottom, because I have a 2x at the bottom. Note that 1 minus x minus root, I guess I'm gonna write down the first term of this. Note that the constant term of 1 minus x minus root x squared minus 6x plus 1 is in fact 0, is 1 minus 1, which is 0. Thus, x in the denominator allows the power series to converge for all x with x less than 1/10. Okay, so suppose this power series f of x for f of x is in fact just sum of bn x to the power of n equals 0 to infinity. So suppose that is our power series. Now, our claim is Bn is in fact the same as An for all n. So that's our claim. I'm kind of working backwards. So how are we going to show this one? We're going to show that in fact it satisfies all of the same conditions, meaning that it satisfies the exact same recursion. So we'll go ahead and find B0, we'll go ahead and find B1, and then we'll go from there, and then we'll find the recursion. So f of x is 1 minus x minus the sum x squared minus 6x to the power of n equals 0 to infinity over 2x. Which is, okay, so I'll have to find the first few terms so that I can find B0 and B1. So 1 minus x minus, the very first term is just 1, and I have I forgot the 1/2 choose n in front. So I have the sum 1/2 choose n equals 0 to infinity. The very first term is just 1. The next term is 1/2 choose 1, which is 1/2. And that is x squared minus 6x. The next term is 1/2 choose 2, x squared minus 6x squared. And every term after that would have more powers of x than I need. So that is 1 minus x minus 1 minus 1/2 x squared plus 3x plus, that's 1/2 negative 1/2 over 2 factorial x to the power of 4th minus 12x cubed plus 36x squared plus dot dot dot, I don't need any of those, divided by 2x. So my goal is to show B0 is 1 and B1 is 2. The ones fortunately cancel as we expected. So what I have here is minus x that cancels with that, so I get 2x here. Then I'll collect the like terms for x squared. I have negative 1/2 here. Then I have minus 1/8 times 36 times x squared. And the rest of them are going to be things of higher power divided by 2x. 36 divided by 8 becomes 9 divided by 2. So that becomes yeah, so that becomes minus, let me see, I think I missed the negative sign here. Yes, I did miss a negative sign here. So that becomes positive, yes. Okay. Yes, okay, so that is good now. And I guess the next term is going to be negative as well. So these are all going to be negative, but those are really not going to matter. So what we get here is, so I guess I'm going to write down terms of higher degree. So this becomes 1. So 9 over 2 minus 1 over 2, that's 4. Divided by 2, that's 2. Plus 2x, and then plus the rest of the terms. So that means B0 is 1 and B1 is 2. So that establishes the first two terms. Then we'll show that, in fact, f of x satisfies that key recursion. So the key recursion was what I highlighted up there, what I boxed it up here, which was x cubed minus 6x squared plus x. So x cubed minus 6x squared plus x times f prime of x plus Then I've got 1 minus 3x f of x equals x plus 1. Okay. So for this one, you just take the derivative. So it's pretty straightforward. Just take the derivative and plug it in here and then show that this is true. So now compare the coefficients. Comparing the coefficients of x to the power of n plus 2, we get, so for the first one, since you're taking the derivative, you have to multiply, so you're multiplying x cubed by, you would have to multiply it by the coefficient of x to the power of n, n minus 1. So the coefficient of x to the power of n minus 1 would be bn, and then the term would be nbn minus 6. And then you look at the next term, which would be b n plus 1, and then plus, I guess, 6 n plus 1, bn plus 1. And then the next term, which would be for coefficient of x to the power of n plus 2, you would have to look at the term with x to the power of n, which would be, I'm sorry, the term with x to the power of n plus 1, which would be bn plus 2. So it would be n plus 2, bn plus 2. Plus, then you look at bn plus 2 for 1, then minus 3, and then bn plus 1, and that equals 0. So we're going to simplify this and see what we get. So these two are going to give us n plus 3 bn plus 2, that equals, these two give us 6n plus 9 bn plus 1, and finally the last term is nbn. Thus bn satisfies, this is the exact same recursion that I already had, satisfies the same recurrence relation as an. Therefore, an and bn are the same thing. So we only need to show bn is an integer. Now we're going to start from our f of x, and we will just solve for what we did up there, which was solve for the radical for the square root, and then we'll go from there. So you'll just write down the exact same thing that we did. So at this point, it would be very similar to what we did before. Minus 1 plus x, all of that squared equals x squared minus 6x plus 1. So you simplify, you do exactly what we did, and you end up with, so if you just repeat the same thing, eventually you end up with an plus 1 equals an plus the sum of ak an minus k, k equals 0 to n. Now, by induction, we claim that an is an integer. This is a very simple induction. So the inductive steps are already established, and if all of the previous ones are integers, then an plus 1 would be an integer. So then I would write down the induction very quickly, and that would be our, that would complete our solution.